You are currently the only person in this conference.
Also, I can. Okay. So, welcome everyone. This is lecture number 4. So, I will be starting today. And the lecture today is dedicated to micromagnetics. Let's say that with these units that I'm doing this afternoon, I'm essentially putting together the things that I introduced before. So essentially, I try to do 3 steps. One is to discuss Maxwell equation with magnetic materials. So essentially how we can have magnetized matter described inside the Maxwell equation. So the equation for electromagnetism. The second was to, let's say, evidence the fact that magnetized material are also sources of magnetic field. So would you please open your camera? Can you see me? Because I see myself. No. So let's try to do this. Let's switch off and switch on. Also you know. Okay. Okay. Now I have a feedback of my video. Okay, better. Okay, thanks for noticing this because I had a positive feedback, but okay, and I return back to the magnetostatics. So we discussed the fact that with magnetic material inside the Maxwell equation, we have 2 possible sources for a magnetic field. One that are the currents, we call this external field, or also all the sources that are external to the object of our observation, that is our magnetic body that we want to study, and the magnetic body itself. So we dedicated some time to discuss how this magnetostatic problem should be dealt. And we learned a few things, no? So, for example, the quite important property of the 2 sources that you have for magnetized material. Everywhere you have a divergence, a variation of the magnetization in space. And then you can have something inside the material and something at the border. And the one of the border, we call it the magnetizing field. It does not depend it depends only on the shape of the material. The third step has to do with the energy. So we have seen how we have to deal with the energy of the applied magnetic field, the magnetizing field, that is magnetostatic field, and how we can compute or can express the work that is done by external forces on the system. So to create the external field, to create a magnetostatic field, and the remaining part that goes as internal energy. And this is important from the point of view of thermodynamics, because then we need an energy balance for this. We made also a very short review of thermodynamic issues. So the thermodynamic internal energy and also the thermodynamic potential that we may be interested to use. So mainly related to the quantity that we control. We do control. For example, in magnetic material, it's quite common to control the temperature, for example, in a laboratory, or because our system is in thermal equilibrium with some thermal bath. This is the common option. And also to control the applied magnetic field, because it's very difficult to put constraint on the magnetization. This makes a very big difference between, for example, pressure and volume, where you can choose the quantity that you can control, from other phenomena, for example, magnetism. It's very difficult to put a condition where the magnetic moment is conserved. And now we make the final step. So we, in a sense, put together all these elements in order to formulate a theory that more or less is similar to electromagnetism in the sense that it is a theory for continuum, no? So the space is continuous. We don't want to see atoms, electrons, or whatever. We don't want to see the discrete nature, the discrete quality of materials, but we describe them as a continuum. And this is really a good choice to make, because then we can describe a lot of things in terms of fields, exactly in the same way we do with Maxwell equations. So continuous field, and it's clear that the field that we need to describe is the magnetization field. This theory has been developed, in a series of years, let's say, and it goes under the name of micromagnetic theory or micromagnetics, no? Micromagnetics like dynamics or kinetics, whatever. So let's say we discuss the basis of this theory here, and it's a theory for ferromagnets. So it's the reference theory, essentially, for describing ferromagnetic material. So you may imagine how is important this for the development in so many different aspects. Okay, so let's go to the first slide. As I told you, we want to express the energy of a ferromagnet. We want to give an expression of this energy. But to do this, we want to do this operation in the framework of thermodynamics. And if you remember what we did last time, we discussed the thermodynamic potentials. So they depend on the choice that you want to make on the controlled variables. And we mentioned the Gibbs potential as the one where we have constant temperature and constant, let's say, intensive variable, that in our case is the magnetic field. We also mentioned one thing, that in thermodynamics with magnetic material, where we have to make one choice. So we have to choose if we want to describe as a system the magnetic material itself or the magnetic material and its magnetostatic field. The choice that we make here is the second. Why? Because we control the applied field. So we imagine that we have a ferromagnetic body of certain shape, of certain quality, of whatever material. It can be a piece of iron, it can be a permanent magnet, it can be a sheet, lamination sheet of soft magnetic material. But what we do control externally is the action of the applied field. So all the sources, for example, solenoids, windings, that we have in order to excite. So to change the applied field. So we imagine that we have no control on magnetostatic field at the moment. So the right choice is the following. So to choose the Gibbs potential and to choose as a thermodynamic system, the magnetic material and also the magnetostatic field produced by the magnetization itself. Then we already know one basic relation for the previous lecture, the fact that the Gibbs potential is related to the free energy, so it's the free energy minus mu0 HA times m. that term is exactly the energy of a magnetic moment if I integrate it over the volume. So that's the energy of that magnetic body with the magnetization ebb for being in external field, in an applied field HA. So it's exactly in the spirit of Gibbs potential. No, you subtract, or you sum actually, because there is a minus sign, the energy of the magnetic, the energy for this object for being in its internal field, in its external field. As we discussed the last time, we do not at the moment make any hypothesis of being at the thermodynamics equilibrium or not. So what we do is to add a subscript that is L, well, L stands for the Landau. So we write not really thermodynamic potentials, but we write energies, or let's say potentials, that in principle they are not minimized yet. So we don't know yet if this energy that we compute, it corresponds to an energy minimum. And energy minimum means a configuration which is stable, that do not evolve in time. It's a local minimum of the free energy. And the word local is the really important one. So what we will see when proceeding is that when we have a ferromagnet, we have several configurations that will correspond to energy, to minima of our free energy, of our potential. And that is very much related also to the phenomenon of hysteresis. And we will discuss this in quite detail. So for the moment, let's stick there. So we have chosen Gibbs potential types. So HA and temperature as controlled variables. Then the system, remember, is made by your magnetic material and also by the magnetic-static field that is generated by it. And thanks to this, I have to choose HA as the term which corresponds to in the formulation of the Gibbs free energy. That is the first step. And then we make the second. And the second is still related to Maxwell equations. So as we touched Maxwell equation and the energy of magnetic moment and the energy of magnetostatic field, we already know everything about them. We can already put all these terms there, and then what we will do is to make some reasonable hypotheses on the rest of the free energy. But let's make the step of magnetostatic field. As we said, we want to put the energy of the magnetostatic field as part of the system that we described. So again, we have to add its energy. And the energy, if you remember, we could express this in a quite nice way, because we could write the energy of the magnetostatic field not as for the applied field where we integrate over the whole space, but we can express the energy as an integral over the volume where the magnetization is defined. And the expression is exactly the one written here. What's the most important thing to remember? That if you sum up the two and then you write that the Gibbs potential is given by the sum of a few terms, we can anticipate they will be exchange, there will be anisotropy and so on, and terms related to electromagnetism that essentially comes from Maxwell equation. If there is one thing you have to remember is that the two terms are not the same. There is a factor 1/2 in front of magnetostatic field, of the magnetostatic energy term. This is really important, and the reason is related to the fact that the sources of magnetostatic field is the magnetization itself. So while you compose, if you sum up the magnetostatic field and the applied field, you arrive at the only physical meaning field, which is a total field. So you can sum up the field, but not the energies. So the energies you have taken into account is 1/2. You cannot write just total magnetic field times the magnetization minus sign. That is completely wrong, because it means that you count twice the contribution of magnetostatic field. So I sometimes say, if you have to remember something of micromagnetics, please remember this, that there is 1/2 factor in front of the magnetostatic energy term. So this is quite important fact. I mean, maybe obvious for those that work especially in this topic, but worthwhile to remember very well. Okay, so energy of a ferromagnet. We have already two terms, no? One related to magnetostatic and one related to the possible existence of an external action, the applied magnetic field. But we should have something else, otherwise a ferromagnet would not be a ferromagnet. So only with those terms that you see there, there is very little to do. So where is the internal structure? Where is the interaction between the spins? Where is ferromagnetic exchange? At the moment, there is nothing. So we have to introduce a reasonable description for these effects. And we will do this in the most simple terms. So we introduced the simplest micromagnetic theory for a ferromagnet. But the two terms that we introduce now are, let's say, so, let's say, the basic expressions that we will use will be simple enough but complete enough to describe the majority of ferromagnets, from the super soft magnetic materials to the hard magnetic materials, to the materials that are used for spintronics or magnetic recording. So we will stick to simple terms, but they will be complete enough to describe quite wide range of material, of systems. So to do this, we go to the first, let's say, even I would say preliminary step. No, preliminary because we limit to ferromagnets. So we have an important property that is specific to ferromagnets, that we have already ordered at the microscopic level, even if we do not make any external action. So the spins at the atomic level are already aligned in a certain direction, in a way that if you are able to isolate a small volume of your ferromagnetic material and you look at the magnetization, let's call it spontaneous magnetization at a certain temperature, that value is fixed at a certain value. The orientation of the magnetization could change, but the amplitude is always the same. It will depend on the kind of magnetic material that you're studying and possibly on temperature. This is an important property of ferromagnets. What do we do in micromagnetics is that we assume that the temperature is not changing too much. So we know that this quality, this saturation magnetization, the spontaneous order, will disappear at a certain point. And that point is a critical temperature, the Curie temperature. So when stating this theory of micromagnetism, we say at the beginning that we are at a temperature well below Tc. So we never go to operate close to Tc, because otherwise we need to introduce other phenomena that we are not able to introduce here. So phenomena that in physics goes under the name of fluctuations, of universality. So a lot of phenomena that occurs when the temperature, the spontaneous fluctuation, the energy, the thermal energy starts to destroy this order. So let's stick to temperature well below the Curie point. And then we can simply make the hypothesis that this amplitude of the magnetization vector is a constant. This is absolutely true where temperature is equal to absolute zero. So, for example, take this table, no? You have the three main ferromagnets, iron, cobalt, and nickel. The Curie temperature in Kelvin of the three are listed there. So, for example, if we operate around room temperature, you see that we are very far from that Curie temperature. So we can use safely this hypothesis. Furthermore, the curve of the spontaneous magnetization as a function of temperature, it remains rather flat for a quite wide range of temperatures, and then it decreases quite fast. This, on the right-hand side, is the example for nickel. No? So 628, 27, 28 degree Kelvin of Curie temperature. So clearly, these are all properties that have been measured very carefully in the past. So it's known what is the spontaneous magnetization at any temperature, essentially. So look at iron, cobalt, and nickel. Saturation magnetization at 0K for iron is 2.17. And then around room temperature, assume 290 is more or less room temperature, it decreases very little. The same is for cobalt, and the same is also for nickel. So when, at least at room temperature, for normal application, for application working at room temperature, this assumption of saturation magnetization as a constant, and also not so much changing with temperature, is a very good one, is very good. So we have always the magnetization as a vector with constant amplitude and changing in direction. This changes a lot the situation, because then we don't need to describe a vector with three independent degrees of freedom. We have only 2 degrees of freedom. That is the direction of the magnetization. It means that in a ferromagnet, the magnetization field is a vector with constant amplitude and variable direction. How can be a ferromagnet not magnetized? How it's possible to take a piece of iron and find it not magnetized? Well, it's possible because then this means that you will have regions where magnetization is pointing in one direction and a region pointing in another one. Otherwise, you would not explain why it's zero. That's the enormous difference between ferromagnets and paramagnets. In paramagnets, that is, for example, above the Curie temperature, there is no local order. The amplitude of the magnetization is zero. While in ferromagnet, below the Curie temperature, the amplitude of magnetization is always different from zero and always the same. And only thing that you can do is have different direction from point to point. This observation, let's say, was made by Weiss, and only with this idea, he was able to make the hypothesis, then later verified, that in a ferromagnet you have existence of domains. So regions where the magnetization is saturated, but if you go from region to region, you find different direction. This is exactly what we aim to describe in this micromagnetic theory, but to extreme detail. It's not just the intuition of Weiss, but it goes very, very much into the details. That's a very interesting thing. So exchange. So the fact that this word comes from the exchange between two electrons. So it has to do with the quantum origin of both the magnetic moment of electron and the possibility for them to be ferromagnetically coupled or anti-ferromagnetically coupled. So we stick only to ferromagnetic here. So an energy that tends to keep them parallel. So this energy has two effects. The one that we mentioned here is just the first one. So in a certain sense, is the zero order. So we imagine that the vector is always parallel. So we mention domains. inside the domain, inside the small region, the magnetization vector is saturated and pointing in the same direction. It's not exactly always that, because if you have, for example, the existence of different domains, it means that to go from one domain with up magnetization to the other domains where the magnetization is down, then you have to, to do something. The boundaries between domain is not expected to be on a single layer of atom, because we are aiming to build up a continuum theory. So we want things that changes continuously, and we want to express what is the energy that we have to spend in this non-uniform alignment of the magnetization vector. How to do this? Well, it's not enough, it does not help to start from Weiss's molecular field theory, the one that we mentioned before, no? That essentially just state the fact that there exists the order inside domain, but it tells very little what happens when you go from one domain to the other. So the Weiss molecular theory doesn't help in this sense, because there is no space, there is no neighbor, there is no, what is the force that is trying to put these two vectors parallel rather than anti-parallel? And so we directly take so-called Heisenberg model. In the Heisenberg model, you go directly to atoms, if you like. So you can write it for the spins or also for the magnetic moment, the atomic level. Take a couple. No? Take a couple of two magnetic moments nearby in a lattice, and then you will find that the energy just depends on the product of these two vectors multiplied by a certain constant. If this constant is positive, it means that being parallel is energy minimum. Again, but this is discrete. We have to take one magnetic moment or spin in a certain place or atomic size, or another one, the spin I is one side and the spin J is another side. This is discrete, and this is something we don't want, we don't need. So we are asking, what is the equivalent of the Heisenberg, the continuum equivalent of the Heisenberg model? And this can be worked out. It's quite simple in the end, because if you take, instead of discrete lattice sites, if you take a continuum, then you expand this energy in a sense, you make a series expansion. And this clearly depends on the derivatives. Are the derivatives of the magnetization vectors that matters? And especially since any change in direction will correspond to an energy cost, then we have all the derivative squared. So how in a continuum theory we express the exchange energy as a constant that we don't care, because then we put all the constant out, and something which depends on the derivative of, for example, the x component of the magnetization, everything squared, then x squared, and then z squared. So you have to make the derivative of each of the three components of the magnetization vector and make the square of each of them. That one is a definite positive quantity, and you clearly see that it's minimized only if the gradient are all zero. That is inside the domain where the magnetization is uniform. Every time you tend to rotate one of the components, because you may rotate like this, but you can also may rotate in this direction, and so on and so on. And then you rotate along x, along y, and so on and so on. Every tentative to change the direction of the magnetization vector, m small, costs some energy. The constant which is in front is called A. Exchange stiffness is called exchange stiffness. A quantity that is quantified for most of the ferromagnetic material. We will see the details later. Let's immediately make the second super important energy term, and this is called anisotropy energy. And now we introduce something that again is related to microscopic quality, crystals. So why do not expect some property of the crystal, if we take a single crystal, they will reflect on a macroscopic scale. Crystals can be, can have materials that can have very different crystal structures. And so why not that certain property of the crystal will be reflected? For example, if we have a certain easy axis, an axis which is different with respect to the other, why do not expect that there is an energy associated with the fact that the magnetization is along that specific direction or perpendicular to it? And how to express this anisotropy energy? Well, what you see there is a very simple expansion, quite obvious. So you may say that theta is just the angle formed by the magnetization vector with the easy axis that you may have in your crystal, one easy axis. And then you expand the energy as a power series. You cannot contain you can only contain odd powers of the sign. So you have the K0, which is a constant, it doesn't care. And then you have the first anisotropy constant, K1, multiplied by the sign square. This means that being in this direction or the opposite, for what concern anisotropy is the same, is being perpendicular that accumulates some anisotropy energy. This in the case if K1 is positive. And then you may have more complex high-order terms that very often are needed, and in many cases they are not. This is uniaxial, but what happens to cubic material? Cubic material, it's much more complicated because then suppose I have a cubic crystal, and then I have three main axes. I need to expand this with reference to the cubic crystal. And this is essentially done with the expression that is written here. So again, you have the expression of the energy where we have a constant that you can just put away because we don't need it, a first anisotropy constant, and the second anisotropy constant, and so on with the higher order terms. Again, very often it's enough to take the first. And what kind of phenomena do we expect with the first anisotropy constant? Well, you imagine that K1 may describe situation where, for example, if you have a cubic lattice, then your magnetization will try to be will find an easy axis on the main direction of the cube. And this means that you will have a picture like you will have an energy as this strange picture written here. What does it mean? Is that if the magnetization is along this direction, the anisotropy energy is minimum. So imagine that your anisotropy energy is just a vector described by this strange figure here. The distance of this surface from the center is the vector of this anisotropy energy, as we can only change the magnetization as an angle. So it's clear if you have cubic, you may have the magnetization along Z as an easy axis, along X as an easy axis, along Y as an easy axis. But if you go along a diagonal, for example, the diagonal between Z and Y axis, then you find that the anisotropy is larger. But then if you go along a diagonal, it's even larger. So you will have hard axis and easy axis, being the main direction, the easy axis. What is interesting is that with the expression given here, you can also describe the opposite situation, where the main axis, Z, X, and Y, are the hard magnetic direction. So the magnetization, for example, in this case, will tend to stay with low energy along the diagonals of the cube. And this is just described by the fact that K1 is negative. So K1 positive with the cubic, it means that magnetization will stay along the main axis of the cube. And this is typically what happens, for example, with iron. And otherwise, if K1 is negative, the magnetization will tend to stay along the diagonal of the crystal, of the cube of the crystals. And this is a typical situation for nickel. So it's not that strange. So quite common material have quite different anisotropy energy. Yes, for example, this is an example of the crystal structure for BCC iron, HCP cobalt, and FCC nickel. And there you also find the corresponding anisotropy constant. So iron is BCC, as I told, well, as you see there, the anisotropy constant, joule over cubic meter, so it's an energy density. It's an energy density. Is this number written there? Not so small, by the way, and it's positive. So it means that the magnetization will try to stay along the main axis of the cube. At the complete right, you have nickel, which is FCC, and K1 is negative, much smaller, by the way. So nickel is much soft materials. I mean, there is no very big preference of being in a certain direction or the other. And so you can immediately associate the idea of magnetic anisotropy with being soft or being hard. So materials that are that prefer very strongly a certain direction, very difficult to leave that condition. So there are possible candidates for permanent hard magnetic materials. Those that can have any direction of the magnetization with no reference to anything of the crystal, then good candidate as soft magnetic materials. Candidate, because then other conditions are needed. Cobalt, which is hexagonal, it's uniaxial, it's not cubic. The magnetization will try to stay along the C-axis of the hexagon, and the anisotropy is quite large. So the cobalt itself can almost be an hard magnetic material. So it has an anisotropy which is 10 times those of iron and 100 times the one of nickel. So in comparison with the other quite common soft elemental ferromagnet is the one that has a very most important anisotropy. Then you may imagine that's alloying and putting other elements. Anisotropy is the anisotropy constant is a value that changes very much, and it has also been the subject of enormous investigation in order to develop materials with very strong or very small anisotropy. Okay, so let's go back then to the mathematical formulation. As we said, we want to write this energy, but then what to do? We simply take the exchange energy term, the anisotropic energy terms, and two terms that comes from Maxwell equations, put them together, and we write what is called the micromagnetic energy functional, if you like, functional. Because one thing to notice is that while anisotropy and applied field, they just depend on the magnetization vector in that point. So they are local terms. The magnetostatic field and the exchange, the magnetostatic field energy and the exchange energy, they are not local. They do not depend on what the magnetization is doing one place. The exchange, it depends on the derivative. And the magnetostatic, so it said that it describes a sort of a short range interaction. But the magnetostatic field HM itself is the solution of the magnetostatic problem, but we know that the magnetic field, the solution of every magnetostatic problem is a, let's say, it corresponds to long-range interaction. So magnetostatic field is something which is strongly non-local. So the position of a domain ball on a corner of a certain material, it will influence all the rest. So it's a term that is really tricky to get into account. Anyhow, even if we are different quality of like that, this is not that important, no? Because what we need at the moment is to understand if we have solution that correspond to energy minima. Energy minima means local energy minima. So consider that your material could assume a certain configuration of magnetization. For example, one domain up and one domain down on one side. This is already a configuration, but how can I know if this is a solution or an energy minimum of this functional here? Well, from functional analysis, we know that we have to minimize this Gibbs free energy. And specifically, we have not only to make the derivative, but we have to make what is called functional derivative. That is, we make this derivative around a certain solution and verify that this is a minimum. But this is the condition. So we need to look for extreme of this energy functional, first of all. And now, yes, essentially, this is the point, no? This person here is William Fuller Brown, that essentially is the one who developed micromagnetism. So all what I discussed now as a passage and way to formulate this energy functional was more or less put together by him. And he also made an important passage of this because he discussed the idea of minimization, functional minimization of this functional. And what you find at the end is that, and this is quite important, that the possible solutions of these micromagnetic problems, they always have to satisfy to what is called the Brown equation. That is, instead of the field, Brown introduced what is called an effective field. So an expression, a value, a vector field that, I mean, you can compute, is not a magnetic field only, is a mathematical combination of the contribution of several terms. But the important thing that in order to be an energy minimum, a configuration must be with magnetization parallel to the effective field. That is, the external product of effective field times the magnetization vector must be zero. This is what's called Brown equation. Now, we have no time to make the derivation of this effective field, but let's give a look, because this is very simple, written this way. The effective field is a sum. Let's start from the end. Is the sum of the applied field, the magnetostatic field. Then if now, yes, if you combine them, you have the field of Maxwell equation with magnetic material. Now, yes, they can be summed in the expression of the effective field, but not in the total energy. Then you have two extra terms that in, let's say, in a quite confusing way, we call field, but they have nothing to do with Maxwell equations. So they both are the derivative of the anisotropic energy or the exchange energy with respect to magnetization. So they have nothing to do with Maxwell. They are simply put there, let's say, they are sort of effective force acting on the magnetization. But then it became, let's say, quite common to measure them in the units of a magnetic field. Let's accept this because they are summed to the magnetic field H, to the true magnetic field HM and HA. Very nice. So not only, so we know that in order to be a stable configuration, a magnetization configuration must satisfy Brown equation. This is an energy minimum, and this means that the magnetization will be aligned to the effective field. Then Brown also developed the boundary conditions that are also that has to do with the exchange that we do not discuss now. So let's proceed a little bit, but can we understand which is the main term that is important here in this micromagnetic energy? To do this, we would like, for example, to express this energy in dimensionless form. And this can be done very easily. Why? Because we have saturation magnetization there. Saturation magnetization, we said, is a constant. So we can build up the product of mu0 ms square as an energy density, and then normalize all the energy by this quantity here. And then instead of making an integral that gives an energy, we go into an integral of dimensionless quantities. But if the quantity are dimensionless, then we can understand something on the typical length of the typical length, because then it remains only to make an integral over space. By doing this operation, you immediately introduce two typical lengths, very important in micromagnetics. That is what you find here. So, in front of the exchange energy term, you find what is called the exchange length squared in this case. In front of the anisotropy energy, you essentially find this ratio between, let's call it, the intensity of the anisotropy energy and the intensity, in the end, is the magnetostatic field, because magnetization essentially it goes there. And then the other magnetic term, as you see, they are not multiplied by anything. So they are normalized as they are. If we combine the two, we can also introduce another length that is very much related to the domain wall width, so quite important, length that is given by the ratio between the exchange and the anisotropy, square root. So, as you see, associate mu0 ms square to magnetostatic, K anisotropy to the strength of anisotropy, A to the strength of exchange, and then you find that there are three main energy terms that are competing. These are the three that tells us if we have large domains, small domains, soft magnetic material, hard magnetic materials. In the end, much of the domain structure of materials is dominated by the typical ratio between these lengths, and also by the system size, by the way. Let's have a look on how the parameters, this micromagnetic parameter, changes from material to material. Here we have a very nice list of different materials. So iron, cobalt, and nickel, elemental ferromagnet. Gamma iron 203, which is a ferrite. Chromium dioxide is a material that used to be one of the material for recording tapes. Then these one are the barium ferrites, so magnetic materials, insulators, quite common, quite cheap. And then three materials of the family of hard magnetic materials, rare transition metals. The typical value of magnetization saturation are written there. And then what I would like you to notice is that here there is a list of this change stiffness, measured in joule over meter. And if you see, they do not change that much. They do not change that much. They change over maximum 1 order of magnitude. I mean, they are a little bit small for the oxides, but for the metals, more or less, they have practically the same value. So the exchange parameter is not changing that much between different ferromagnetic material. What is changing a lot is the anisotropy constant. Here it's in the unit 10 to the 5th joule cubic meter. And then you see that typically soft magnetic material, nickel, ferrites also are not so hard, have very low values. And for the hard magnetic material, for example, neodymium or boron, samarium, cobalt, they have very huge value of magnetic anisotropy. So this is the parameter that tells you that these are the good candidates for hard magnetic material, for permanent magnets, where there is one direction of magnetization that would not like to be changed. As a consequence, we can also compute the exchange length, which is something in the nanometer scale. So this is the typical scale of micromagnetism. We describe things of typically in the nanometer scale, and the typical domain wall width, if you like, as the second one, it depends on anisotropy, then we can have a lot of variations. For example, for soft magnetic materials can be quite wide, quite big, and while for hard magnetic material it can be very, very small. So we do expect domain walls of completely different width for different kind of materials. So still, I think 10-15 minutes to finish. Let's say this is something that you find in the book of Giorgio Bertotti. This is a very interesting, let's say, test of this idea of using, describing the competing energy terms. And it is put in practice the idea of before. So when you have exchange energy, anisotropy energy, and magnetostatic energy, all three together, and you want to evaluate them in quite, let's say, simple case, where you have a magnetic material which is a sort of a dot or a small sphere with a typical radius r, because the length that was missing, the dimension that was missing, was the dimension of the sample. So we have to compare this length with the typical sample size. For example, this you find, as I said, in the book of Bertotti, and he did this quite, let's say, simple evaluation. So he selected three types of domain structure. Case A is a single domain. So the whole sphere, the whole material is all magnetized in a given direction. In the case B, you have a domain wall. So you have one domain with up magnetization, another domain with down, and some transition region. In the C, you have what is called the vortex. So you imagine that the magnetization is free to adapt to any change without spending too much in energy. And so what happens? That we discussed this. Magnetostatic, let's say, demagnetizing field depends if we have a change of magnetization at the surface. But if we keep the magnetization always parallel to the surface, not perpendicular, parallel, then this demagnetizing is minimized. Well, it's clear that in the first, A, exchange is zero, but and anisotropy also could be zero if you are in the right direction. But you have a lot of magnetostatic energy because the magnetization. In the second, you have to pay for the domain wall, and you pay in exchange and anisotropy. It will not satisfy neither one, neither the other. But you gain in magnetostatic because the global magnetization is zero. In the third, again, you gain in magnetostatic because you have very little magnetostatic field to generate or nothing. But you pay in exchange, especially because you may imagine that you pay in anisotropy, especially because you need to make a vortex, so to have the magnetization in all directions. What is interesting to do is to take two cases. One in which the anisotropy is typically small, and one is typically hard, left and right. If the anisotropy is typically low, then it means that K is very small, the K that you have in the table there. And then for the tree configuration, you can compute approximately the energy as a function of the radius. And then it's clear that you can look at which is the configuration that for a given radius is the minimum energy. And you discover a lot of interesting things. So, for example, for soft magnetic material at a very, let's start from the other. For soft magnetic material at a very large scale, the energy minimum is given by multi-domain state. In fact, all material, soft material, build up domains. This is the most common configuration for typically large size. There's nothing to do. If you decrease the size, then there is another configuration which becomes minimum, and this is the vortex. So at a certain small size, and we are already in the nanometer thickness typically, as you see below, the vortex is the first configuration that becomes stable. And you have still to decrease the size in order to have the single domain for a soft magnetic material. It's not that easy. Completely different if we take a hard magnetic material. As you see here, the vortex will never become stable. So if the typical size is quite large, you have multi-domain state. And at a certain point, the single domain can become the minimum energy state. And this is a very good news, because if we want to build a permanent magnet, not only we need a very large anisotropy, and this is the case, but we also need to have a small grain size, because only in that condition we could have grain as single domains. Otherwise, if we put a field, this multi-domain state will change magnetization quite easily by the motion of the van Waal. The same thing is for soft magnetic material. If we want a soft magnetic material, we cannot put too small grain size, because otherwise they will stick to this strange configuration, single domain, vortex, that are not easily changed. Much better is to have a very large and extended domain structure that we can magnetize very easily. So this idea of competing energy terms in reference to microstructure can tell us something of quite of interest. This is just to mention that this micromagnetic Brown's equation are the basis to study a lot of different configurations. A lot can be done analytically, especially for those that have studied the domain configuration, the domain walls, and so on and so on. So Michaela will touch this later. And then, obvious to mention in a certain sense, now people is taking this equation and solving them numerically. So there is an entire research sector that is using, let's say, the numerical implementation of micromagnetics. So, for example, for dots, for small domain structure, especially for nano-sized, you can compute and then see if the computation that you make are obeyed by the system that you can produce at the nanoscale. To conclude my part, I still add something quite, let's say, this is a sort of conclusion of two things that I said before, but Michaela then will touch this in more detail in one of the last lectures. So we said everything, all we said up to now, it concerned statics. So we said we would like to know what is the equilibrium configuration of the magnetization. Then what happens if this configuration is not the minimum energy one, or if we apply condition in such a way that the configuration would like to change. We have to allow for this change. And But this change, in order to describe this change, if you change energy, for example, then we have to describe how energy is dissipated. And this is damping. So without changing too much the Brown equations, the Brown statement of the micromagnetic energy, we could very easily add something. So if we have a configuration which is not an energy minimum, and we want to reach the minimum by helps to a certain dissipation mechanism, even if we don't know the detail of this dissipation mechanism, we can already say something. So, for example, we can say that the equation written here, take the derivative of the variable of the magnetization equal to the effective field. If you think about it, then this is exactly a condition that brings you, this is a condition that if the effective field is parallel to the magnetization, then you don't have any change, because we can only have a rotation of the magnetization will not change in modulus. And the second important thing is that this choice is perfectly coherent with the fact that in order to reach energy minimum, we have always to dissipate energy. That is, for dissipative processes, the variation in time of the Gibbs potential must be proportional to the entropy production rate. So it's something that has to be always positive. If you take an equation like this, then you can prove then any dynamics, any tau that you put there, it gives always dissipation, always an increase of the heat that is generated. And this is exactly what you need. Even if you don't know too much about where this damping process comes from. This is important because it is actually the basis of the description of magnetization dynamics. So magnetization dynamics, it contains one term that we will see that has to do with the torque. So it's completely dynamical, and another which is completely phenomenological. But it's phenomenological in a way that is perfectly compatible with thermodynamics. And this is enough for the moment, even if we don't know the details of the damping processes. So what is the dynamic I was referring? It's precession. So we said this at the beginning of a lecture before. So why we do have a magnetization precession? Because the magnetization is related to an angular momentum. So if we have a torque, then we have the change of the angular momentum with time. The torque, we know from one of the first lecture, is related to the effective field, to the magnetic moment. But the point here for magnetic material is that the magnetic moment itself is due to an angular momentum. If we put together all these things, then you end up with what is called the precession equation. The precession equation. This means that if you have an effective field which is not parallel to the magnetization, not only you have damping, as we said before, but you have also precession. Precession, it means that the magnetization vector will remain constant in with the component which is parallel to the magnetization, but with the effective field. But the component of the magnetization which is perpendicular to the effective field will start to rotate. Precession. The speed of rotation, it depends on what is called the gyromagnetic ratio. So it's known that for classical, and the gyromagnetic ratio is the one which is written here, gamma. It's known that for classical particle, we have G is the Landé-G factor equal to 1, and for the spin, this is almost equal to 2. It's a correction that, again, it depends on the phi structure constant, but this is essentially equal to 2, Landé-G factor for the electron. Then it turns out, so the gyromagnetic ratio for the electron is negative because charge is negative. But it very much used to take out this minus and to write the equation in this way. So gamma very often is reported to be a positive quantity. So how much is this gamma for the electron? Is what is written here. So gamma over 2 pi is a frequency over Tesla, 28 gigahertz Tesla. So this effect, this phenomenon of precession of magnetization for the ferromagnets with the spin, with the electron spin, is in the gigahertz range, several gigahertz. So it's an effect that it's very much studied because also communication are used in this range. So it's there is a quite large amount of effects that are that employs this precession of magnetization. I'm not touching this, and maybe Michaela will discuss this a little bit toward the end. So if we want to put together precession dynamics and damping dynamics, then you write this famous equation of Landau, Lifshitz, and Gilbert. There are two ways to combine them. They are called the Landau-Lifshitz form and the Gilbert form. So I don't want to go too much into the details here. You will have this in the slides. Let's say that this is interesting, especially for those that are more or less aim to work on this. But this is mainly to know. So the two different forms are mathematically equivalent. And the equivalence is given by these relations. So it's a gyromagnetic ratio for the electron that is changing a little bit from one to the other. So I have also a slide for the discussion of the different meaning, but I think I can. I don't want to discuss this too much into the details. It's just a combination. It describes how you can combine damping and precession in an equation. And I go to the end to list my references. So where you can find these things. The book Micromagnetics is by this William Fuller Brown, a little bit historical source of 63. Bertotti, I took most of the material from there, and the book is quite well done for all this energy and micromagnetics, even without any specific application on lyrics, but at least more or less what I've explained here. For those that are possibly interested into dynamics and what is called ferromagnetic resonances, I mentioned two very nice books here. So very much specific on the topic concerning spin waves and ferromagnetic resonance that maybe Michaela will touch toward the end. Okay, and I stop here. Thank you very much. So we did 1 hour and 15 minutes. I think it's okay to make the break and not to go too long. If you have a question, you can ask. I see Michaela already there. Do you want to stop recording, Michaela?
Okay, so first question, what is the origin of magnetic moments in matter and what kind of magnetic moments exist? Please, if somebody wants to reply to this. Nobody wants to reply. Okay, so I will do this summary, of course. So the origin of magnetic moments is, of course, in quantum physics, and the magnetic moments are properties of the electrons. So we have the orbital angular momentum L, and we have the spin moment S. What is the spin-orbit coupling, which I touched this very briefly? So L and S, since both are magnetic moments, they interact somehow, and classically can be interpreted, of course, by electromagnetism, since you can consider, of course, the electron, which is orbiting, will create a field, and this field will influence, of course, the S magnetic moment, and vice versa. So what describes Heisenberg exchange interaction? Heisenberg exchange interaction, please remind this, is considered a direct interaction between localized moments. So you need to have an overlap of orbitals, very important. So we have localized magnetic moments and they directly interact. Then there exists other type of indirect exchange, and we also touched this in the last lecture. For example, in oxides, we can have super exchange or double exchange. And in metals, we spoke about this RKKY exchange. And here, again, we have localized moments, but they are connected via S electrons or conduction electrons, let's say. So this brings us also to the itinerant magnetism, where we had a 3D for S interaction, for example. And why Heisenberg exchange is not sufficient to describe ferromagnetism and what is itinerant magnetism. And exactly this is the point, because in most of the ferromagnetic materials, the 3D materials, for example, we don't have a very strong overlap of orbitals. So overlap of orbitals is very tiny, and we cannot describe sufficiently by this localized exchange interaction ferromagnetism in iron, nickel, and cobalt. And so this SD interaction is very important. Okay, now let's move on. So today we have to speak about magnetic domains, but I briefly want to introduce this lecture by an experiment, and I will ask you, and hopefully somebody dares to answer, to explain me this very sophisticated experiment that I will show you now. So what we have here are iron clips, you can see. Iron, of course, ferromagnetic material, no? We studied this now several times, we said this. And you see, although it's magnetic, it's ferromagnetic. Now, these clips do not attach to each other. If I would have, of course, a permanent magnet, for example, this one, no? It's a neodymium iron boron permanent magnet, then I can attract this iron piece very easily. You can see it will attach. And now I can also attract this iron clip, no? To the other one. So now it stays attracted. Now, if I remove this neodymium iron boron permanent magnet, then you can see I have it here, and you can see still that the clips stay attached. So let me, can you see this experiment now in my webcam? Okay, so now you can explain what happens here. What did we see? So why these clips do not attach before? If I bring them in the magnetic field of a strong permanent magnet, then they start to act as if they were permanent magnets. Somebody wants to make an attempt to explain this. Of course, you have already a hint. Now it has something to do with magnetic domains. There's alignment in the magnetic moment domain in the first clip because of the permanent magnet. Exactly. So Giuseppe says that in this clip, now we have magnetic domains. Of course, this was the hint that I gave to you. And what do the magnetic domains do? While Heisenberg exchange, which we have, of course, in a ferromagnetic material, would align all magnetic moments in this material, then we would always have that this iron would behave as if it was a permanent magnet. So it should immediately attract another iron piece, no? But it's not like that, because we have magnetic domains, and the magnetic domains will orient in different directions, and overall magnetization might be quite small. When we bring it in the magnetic field of our permanent magnet here, so it would be also sufficient, of course, to keep it just close, then these magnetic domains will orient along the field lines of the permanent magnet, and then they become something like a permanent magnet. No? If I then attach another iron clip to it, then they will stay together even if I remove the field, because now the domain structure will be modified, will be completely modified, and we have a different domain structure that allows that these clips will stay together. So domain structure and domains are very essential in order to describe the behavior of my magnetic material. Otherwise, without domains, I cannot understand the behavior of ferromagnetic materials. And this was clear already to Weiss, who in the last lecture we saw that he found this description of ferromagnetism by the Weiss molecular field. And this was, of course, a very good description from ferromagnetism, but it was not clear exactly how the magnetic domains, how the material behaves, because it was not clear if if one magnetic moment aligns with all other magnetic moments that are surrounding it, then, of course, in iron, all magnetic moments should be always aligned. And so it was an immediate step, for Weiss to say, okay, there must be something different in order to describe the behavior of our ferromagnetic material. And this was done in 1919 by the Weiss domains. So what are Weiss domains? You can see here this picture, and you can already imagine it, that we have several regions in your material where all magnetic moments are aligned, but the different regions are pointing in different directions. And this may lead to the fact that overall the magnetization might be very small or almost zero, let's say. So the question is, of course, what will happen if we bring these domains in a magnetic field? And in order to understand this a bit better, we have to consider, of course, that between the different areas, we have a kind of border, boundary between these regions, magnetic domains, and this border is called the domain wall. And here, of course, in this domain wall, you must have a change of the magnetization direction. If now we want to apply a magnetic field in a certain direction, then will happen that the domains that are already pointing more or less in the direction of the magnetic field that we apply, for example, this domain here in the middle, will enlarge. And this we call domain wall motion. You see now this region here is much larger. Of course, this depends on the strength. How much they enlarge depends on the strength of the field that I apply. And then the second step is this magnetization direction might be, for example, an easy axis direction of magnetocrystalline anisotropy that Vittoria was describing. However, if we increase very much the field, then we might rotate this magnetization out of this easy axis and in the direction, of course, of the magnetic field, because after all, at very high magnetic fields, we will have all domains aligned in the direction of the magnetic field. And this is called magnetization rotation. Now you see that this arrow rotated a little bit and is now parallel to the magnetic field. And both these processes are really essential to understand the behavior of a magnetic material when we bring it in a magnetic field. And this will be perfectly described then by the so-called hysteresis curve that, of course, you heard already about, and which describes the behavior of a magnetic material. And the hysteresis curve we can only understand if we consider magnetic domains. So this is very important to keep in mind. So while in the other lectures, now we started from the fact that we said, okay, Maxwell equations describe very well all kinds of applications that we have in magnetism. But we need the constitutive relations in order to say something with Maxwell equations. The constitutive relations include this relation of the magnetization and the magnetic field. And then we said, okay, we have to understand something about the origin of magnetism. And we understood something. We understood that there are elementary magnetic moments and there's L and S properties of the electrons. No? But all this is still not sufficient in order to describe this relation between M and H and to understand susceptibility. So we have to do this step more. And therefore, this lecture is still essential to understand magnetic materials. So all this describes the magnetization process itself. And since I told you, first of all, domains that are close to the direction of the magnetic field will enlarge very much as a first step. And in order to do this, the domain walls have to move. They have to displace somehow. And the domain wall is the area where the magnetization direction is changing. So in order to understand magnetization process, we have to understand something about domain walls. Otherwise, we cannot go on with this topic. So another thing that immediately will be clear is that we have different kinds of magnetic materials. Materials where it is very easy to move domain walls, for example, and materials where it's much more difficult to move domain walls. If, of course, we can move easily domain walls, then we have a material with a high susceptibility and can be magnetized very easily. And these are soft magnetic materials. On the other hand, we may have hard magnetic materials, of course, where all this process is much more difficult. And again, we will find reasons for this different behavior and the different types of materials in the domain wall dynamics, let's say. So let's consider that we can have, of course, any kind of angle between the different magnetizations in the two different regions, in the two different domains. But the most simple to be described theoretically are 180 and 90-degree domain walls. So this is, when we speak about the 180-degree domain wall, then we think about this, that the magnetizations in these neighboring domains are pointing in opposite directions or anti-parallel. So have an angle of 180 degree. For this 180-degree domain walls, you will very often hear about the so-called Bloch walls and nail walls. What are these different kind of walls? If you think about, for example, a magnetic thin film, it's the most easy way to describe this. Think about a magnetic thin film, and you have the magnetization lying in the film plane. Then you can move in two different ways the single spins in your wall. So now we are speaking only, this is only the picture of the wall inside and how magnetization change. So we are changing from this direction with the magnetization pointing up to the magnetization pointing down. And we do this by rotating out of the film plane. And this is a so-called Bloch wall. On the other hand, for the nail wall, we are rotating in the film plane. So at a certain point, you will find magnetization pointing perpendicular to the initial direction of the magnetization, but lying still in the film plane. And this is a so-called nail wall. Now, since you already heard about the demagnetizing field, now you can imagine maybe that one of these two walls is preferred, let's say, in thin magnetic films. So the one that is preferred, of course, is the one where the magnetization is not going out of the film plane. Because if magnetization points out of the film plane, then we will have a strong magnetostatic field here. And this is energetically not that favorable in thin magnetic films, unless you're in certain situations that we are studying recently very much. Okay, what is the domain wall energy and what is the domain wall width? So let's analyze a little bit more these domain walls. So the domain wall itself, no, let's make a summary, no, is this gradual change of the magnetization direction from one domain to the neighboring domain. So in order to calculate domain wall energy, what do we need? Of course, we have again to make some energy balance between competing energies. And the competing energies in the most simple case that we have to consider are the exchange interaction. So let's consider localized spin magnetic moment, let's say, that interact by exchange. So they want to be parallel. And the other energies, what you heard before, might be anisotropy. So if you have a preferred direction of your magnetization. So moments parallel are acting against a force that wants to keep your magnetization in a certain spatial direction. And this can be, of course, up or down, let's say in this direction. Now, let's start with analyzing this exchange energy. So let's consider a wall that consists of n spin magnetic moments. And we are considering, of course, a 180-degree domain wall. So we are changing from up to down at the end. Let's consider, of course, we have to have a gradual change between these spin directions. So we will have a small angle theta between two neighboring spins S1 and S2. And exchange energy, if you remember, will be minus 2J S1 in S2. Of course, then we can consider the angle theta here. And this energy, of course, will be minimum if the theta is equal to 0, so if the spins are parallel. So if we have n different spins, then let's say the angle between two neighboring spins will be pi divided by n. If n is large, we can consider theta to be small, and we can make a Taylor expansion of the cosine of theta. This is just now for simplifying this, this calculation, of course. So then we can calculate a delta exchange energy between neighboring spins. And this is simply J times S square times pi divided by n square, coming from this Taylor expansion. So now we multiply by n in order to get the total energy of the domain wall, exchange energy of the domain wall, and you get this expression. So what we see immediately, of course, this is a positive energy, and n, if it's going to infinite, this energy will become minimum, will become 0. So what exchange energy wants is to enlarge the wall as much as possible, to have very large domain walls, possibly an infinite wall. Now let's consider anisotropy energy, and let's take the example of magnetocrystalline anisotropy, for example, a uniaxial anisotropy in a certain spatial direction, as it is the case for cobalt, which has a hexagonal crystal lattice. And here we have the easy axis in the direction of the Z axis and a hard plane perpendicular to it. So anisotropy energy, you saw before, in this case can be described in this way, and we simplify it just considering K1, the anisotropy constant, and here in this case it would be about 5 times 10 to the 5 joule per cubic meter. So this is just to give you a feeling about the numbers. Now, in a very strong hard magnetic material, this would be 70 times 10 to the 7 joule per cubic meter, as for example in the case in the samarium cobalt 5. Okay, so let's consider this as a term as describing our anisotropy energy. Again, of course, we have here our angle theta between the different spins. And now, in order to calculate this more easily, because you see here, we have a sum, of course, between the spin and the easy axis. So you have a sum over all spin moments that you have in the wall. If theta is small, let's say, you can consider this as an integral, but we are doing this really only to simplify the calculation now in order to get an immediately end result. In this way, again, you use a Taylor expansion of the sine square theta, and you get your anisotropy energy. We have still to multiply by a volume, because this is a volume. This is an energy density, let's say. So I did not mention this at the beginning. So we have to multiply by some kind of volume. In any case, what we find immediately is that anisotropy prefers an infinite small wall. So possibly a 0 wall, an immediate change from the easy axis again in the easy axis, but now pointing down, while for the magnetization was pointing up. So if n is 0, then this will be a minimum. Okay, let's put these two energies together and we have our domain wall energy. This is now a surface energy, so you have to multiply, you have to divide by an elementary area, let's say. If you think about the lattice with an lattice constant of A, for example, for your spins, then you can do this easily in this way. So this is the domain wall energy, and what is the width of the domain wall? In order to get this, we have to minimize the domain wall energy with respect to the number of spin magnetic moments in your wall. So you put the derivative equal to 0, and then you get, we can insert n in your domain wall energy, and you can use the exchange stiffness that also Vittoria used for describing the exchange. So instead of using J, you will use A. And then we can have a very simple, nice expression for your domain wall energy. And this is pi times the square root A times K, the anisotropy constant. So this simple expression you can remember. And of course, you can calculate also the domain wall width. And this is pi times the square root of A by K. Okay, so two things to notice about this. We have, so our domain walls have a positive, always positive energy. And it's the higher is the exchange and the higher is the anisotropy. So the question is, if I have to introduce a domain wall in a material, which costs me energy, then why should I do that? So there is actually no reason to do that. No, I always have to increase the energy of my material in this way. But there's one thing that we did not consider. We did not consider all energy terms in this reasoning. We only calculated, of course, domain wall energy now, but the overall your material has other energy terms. And one most important, which explains us why domains form, is the magnetostatic energy. So as we saw several times now already in the lectures, if you have a magnetic material which is uniformly magnetized, then you will have a strong magnetostatic field outside, and inside this will be manifested as the so-called demagnetizing field. You can also describe this mathematically. Of course, you saw already that the demagnetizing field cannot be calculated very easily analytically, but in simple cases it can, and these are ellipsoids, for example, and for a sphere there's a simple expression where this demagnetizing field is minus 1/3 times m. Okay. Once we know that, we can think about that if we introduce one domain wall in your magnetic material, then you will drastically decrease this magnetostatic field. So you will have to use this energy of your domain wall that we calculated before, but we will reduce very strongly the energy that is needed for creating this magnetostatic field outside. In fact, we are creating here like a magnetic circuit, let's say, and magnetostatic field is coming out only at the surface. And this is the reason why we have magnetic domains. So in order to reduce magnetostatic energy, of course, you can think that you can reduce even more, creating an array of domains as you can see it here. So if you think that this is a cross section of your material, cutting through your material, then you can really create these tiny magnetic circuits here where the flux is almost completely closed inside this magnetic circuit and is only coming out here at the surface where we have these domain walls between these 180-degree domain walls. So how much this is preferable, of course, depends on how strong is your magnetostatic energy. These domains, by the way, are called closure domains. And just as a remark, this is very important when you want to give a look by imaging to these magnetic domains, because if you look on the surface, you may find a domain situation which is completely different from what you have inside your bulk material. So in bulk materials, this might be a problem to understand something about the domains inside. Now I told you that the domains are related to the magnetization process, and in fact, they are describing the magnetization process. So you can understand the hysteresis curve. So hysteresis curve, I already mentioned this at the beginning. We have two very important features. which are coercivity, which is the field at which the magnetization becomes zero, and remanence, which is the magnetization when the field is zero. So this hysteresis curve, of course, describes my magnetization process. So when I'm coming, for example, from high magnetic field and I lower the magnetic field, then I will arrive first at remanence and the field is zero. Then I can invert the magnetic field, increase it again, I will arrive to coercivity and so on. So, and of course, the inverse process, so coming from the negative magnetic field, is not going on the same path back as it did before. And that's why we have hysteresis. So in this very steep area of the hysteresis curve, we have mainly domain wall motion. So this is the area where the domains enlarge and the domain walls move a lot. And this gives you this steep behavior because it's much faster and energetically it costs less energy, let's say, to move the domain walls. In this area, the hysteresis curve here becomes very flat, and here is where magnetization rotation dominates, because to rotate the magnetization out of an easy axis, for example, is rather difficult and needs high magnetic fields. So if we zoom out this area here, for example, this deep area, a lot, then you will see that this is not a smooth curve, but has a lot of tiny, tiny steps. You can see here in this picture, these tiny steps. And this is not because we cannot perform the measurement very well, no. These tiny steps you will always see, and they're not directly related, let's say, to the field steps that we do when we increase our field during the measurement. These steps are related instead to the energy landscape that we have inside the material. So if we want to move a domain wall, then this domain wall has to overcome certain energy wells. And this energy well distribution, this energy landscape can be rather complex. And this is, of course, the reason also why we see hysteresis. Now, this overcoming of energy wells is always an elementary element for having hysteresis. Here you can see this energy landscape correlated to the domain wall motion. So when we are above the energy, if this is, for example, your energy that you have due to the field that we apply currently, then you will have domain wall motion if you're above this energy, and your domain wall will stay still at a certain point if you're below this energy well. You have to increase, of course, your field in order to overcome this domain wall, this energy well, and to move your domain wall again. So this causes a kind of avalanche-like domain wall motion. And this avalanche-like domain wall motion, which is the origin somehow of hysteresis, is caused by a lot of pinning centers, And pinning centers can be, for example, strains, so related to magnetoelastic energy, or can be inclusions related to magnetostatic energy. For example, non-magnetic inclusion will also pin your domain walls. So this brings us to a very important fact, that hysteresis and the hysteresis curve do not only depend on your material, so on intrinsic properties, let's say, of your material, but it also depends on microstructure. And microstructure is a kind of extrinsic property of your material because you can change it. Microstructure, grain size, for example, can be changed by the processes that we apply during preparation, something like annealing temperatures and so on, annealing times. No? Impurity, defects, also they are influenced very much by the preparation technique and so on. So we have hysteresis is in part formed by the material itself. No? For example, saturation magnetization will be completely determined by the material that you have. But other properties are determined by this microstructure. For example, coercivity is very much determined by microstructure. If you have a material that potentially might be a permanent magnet, so having a strong, a large coercivity, then performing certain annealing processes, you will find that you can reduce it to be a soft magnetic material. Because being a hard magnetic material or a soft magnetic material, this depends really a lot on these extrinsic properties. I would like now to show you that this avalanche kind of motion of the domain walls, we can also listen to, and this is called this Barkhausen effect. And I'm sorry for who cannot access to YouTube, that have to be a bit patient and wait until I show this this video, because all these videos are on YouTube, unfortunately. But I will share with the other ones this video, which is very nice. And we see again our Professor Lewin. And he will show you this effect of the Barkhausen. Okay, so I like this very much, this demonstration, and I hope you enjoyed this also. So the fact is now what you're doing here is at each step that you have, if you take the derivative, which would be the induced signal now that you have in the coil, then of course you can get a noise in a loudspeaker. And I hope this was very clear, was described very clearly. Now, before going to the small magnetic particles, I also want to show you maybe another quick movie which demonstrates which shows, illustrates is the right word, which illustrates the domain wall motion in a material with defects. Because I described it, but maybe it's nicer to imagine something with a very, very simple picture. And this is a simulation that was done by my colleague Gianfranco Dorin a long time ago. A very simple simulation. You can see here the domain wall that starts to move in this material with defects. Now let's go, and you see that the domain wall will behave like this. Now it might, for example, stick for a long time at the defect, and then it will go on. And then it sticks again in certain points at the defect, and then it goes on. Of course, this is while you're increasing field, and you have this domain wall bowing very often. So this is the avalanche-like motion of a domain wall. Okay, let's stop sharing. Now let's move to small magnetic particles. So since magnetostatic energy is a volume energy and the domain wall energy you saw as a surface energy, both scale with the dimension of your magnetic material in different ways. So here, magnetostatic energy, of course, is proportional to the Q of the diameter if it's a spherical particle, while domain wall energy scales with the square. What does this mean? As a consequence, no, we will have that usually magnetostatic energy is much higher than the domain wall energy, and that's why we have actually domains. No, we said in order to reduce magnetostatic energy, we introduce domain walls. But on the other hand, if you go below a certain critical diameter, then you see that domain wall energy is higher than magnetostatic energy. And in this case, it's not favorable, it's not convenient to introduce a domain wall in your spherical magnetic particle, as it is shown here. So this is called the so-called single domain particle, which is so small that we prefer not to introduce a domain wall and prefer to have it uniformly magnetized. And now we want to calculate, let's say, the diameter, this critical diameter, or critical radius, with a very simple picture. And for this, we compare the two energies, one, the energy of a uniformly magnetized spherical particle, and the energy of a particle which is divided in two halves by a domain wall. So for the uniformly magnetized particle, of course, you have to calculate here magnetostatic energy, and this is quite immediate. For our divided magnetic particle, we have to introduce this domain wall energy times pi r square. Plus, we have, of course, to add a little bit of magnetostatic energy. And let's take as an approximation half of the magnetostatic energy of the completely magnetized material. So at a certain critical diameter radius, we will have that these two energies are equal, and from this we can calculate this critical radius. and you see this expression here. If now we consider that the domain wall energy is pi times the square root A times K, then we will get this final expression, and we understand that this critical radius, of course, depends on exchange, on anisotropy, but also on saturation magnetization. So this is the particle size in order to have a single domain particle. Now, this brings us to the Stoner-Wolfert model, which is a very important model in magnetism, and it's also very much considered in order to understand better hysteresis processes. And here we consider this so-called single domain particle. Let's see a little bit what is describing this Stoner-Wolfert model. So if we have a single domain particle, let's consider it ellipsoidal. And if it's ellipsoidal, we will have an easy axis along the ellipsoid. And this is an easy axis which is not created by magnetocrystalline anisotropy, but by shape anisotropy. So due to this elongated shape and due to this, the effect of the demagnetizing field, we will have an easy axis along the long axis of this ellipsoid. Now we consider any kind of magnetization direction and a magnetic field that we apply along a certain direction. And what we want to calculate is a kind of hysteresis curve. So how will magnetization change when we increase this magnetic field? Of course, in order to calculate this kind of hysteresis curve, we have again to minimize somehow our energy of this magnetic particle. And again, we consider two different types of energies. We have the anisotropy energy, let's say, and the Zeeman energy, let's say, the energy of the magnetic moment or magnetization of this magnetic particle, single domain particle in the magnetic field. Now let's consider only two simple cases in order to calculate this energy minimum. And these two simple cases are that we apply the field first in the easy axis, so theta is equal to 0, and the second case is that we apply the field perpendicular to the easy axis, so theta is pi half. Let's start with theta equal to 1, so we apply the magnetic field in the easy axis. Again, we have this equation, now it's simplified by theta equal to 0, and we can calculate by using this derivative with respect to phi, the angle, the possible solutions. So we have one solution, which is immediate, that sinus phi is equal to 0. And this means that phi has to be 0 or pi. Solution 2 is that the cosine phi is equal to this expression here. And this expression includes HMS and K, the anisotropy constant. Let's try to plot these solutions in order to understand something. And we plot this, as I told you here, in the way as if we would like to plot the hysteresis curve. So on one axis, on the y-axis, we have M, and on the x-axis, we have H. Of course, the maximum values that we can take are the values MS and minus MS. And if we want to plot the solution 1, then we have immediately these two lines, which are phi equal to 0 and phi equal to pi. Now the second solution instead is this one. It's a line with a certain slope. Are these possible solutions also really energy minima And this we can understand only if we do the second derivative, and this has to be larger of 0, of course. And so if we try to calculate the second derivative and we use the solution phi equal to 0, then we will find then this solution is a stable solution as far as h is larger than minus 2k divided by mu 0 ms. So above a certain value, we will have this stable solution. On the other hand, for the solution pi, we have that h has to be smaller than 2k mu 0 ms. For solution 2, instead, we would have that this is only stable if h is larger than this h squared is larger than the square of this value before, which would mean along this line here outside a region which can be a solution, because this would be values, all values larger than ms, and we said we can go up only to the value ms. So the value, this strange value here, I call it now already HC, because it indicates us the coercivity of this kind of hysteresis curve. So HC is equal to 2k divided by mu 0 ms. And you can imagine now that the situation is the following. If you're coming from a high field, magnetization will stay always at saturation magnetization until we invert the magnetic field and we reach minus HC. Then immediately we will switch to the solution 1 with phi equal to pi. And if we increase further, we will stay in this solution. If we go back instead, then we are coming back from negative ms, and we switch again at HC to the next solution. And this, of course, is a typical hysteresis curve. We call this very often a bistable unit because it's an elementary unit for having hysteresis with a coercivity HC. So imagine here in this particle, you start from a high magnetic field applied in this direction, you decrease the field, magnetization stays in this direction unless we invert the field and reach a field minus HC. Then immediately the magnetization will switch in the opposite direction. And this is something that is reasonable, and we saw also this energetic behavior of a domain wall. No? Anisotropy always wants an immediate change, no anisotropy energy of your magnetization. It does not want any intermediate steps of magnetization. So staying always in the easy axis of anisotropy. Let's take the second case where we apply the magnetic field perpendicular to the easy axis. Again, we do all this same calculation. Let's move through quite quickly and give a look immediately to the solutions. So we have again solution 1 along minus ms and plus ms, and solution 2, which has now a positive slope. So which are stable solutions? Solution 1 for phi equal to 0 is stable if h is larger than this value hc. Phi equal to pi is stable if h is smaller than minus hc, so in this region. And the second solution is now stable everywhere where h square is smaller than this value hc square, so here in between. And so now you can understand that here we don't have hysteresis. So if we apply our magnetic field in this direction and we come from high magnetic field, we reduce our field, then magnetization will stay until hc in this direction of the applied magnetic field, but then there will be a gradual change of m going to the other direction. And here we don't have hysteresis. Of course, now you can consider that there are all other angles theta. And if we want to think about a polycrystalline material, so where we have a lot of these single domain particles, let's say, close to each other, pointing in all kind of different directions. If we then apply a magnetic field, then we will have a polycrystalline hysteresis curve, and this would be kind of average of all different directions of our Stoner-Wolfert model. And in this case, you will find that remanence corresponds to 1/3 of your coercivity. Of your saturation magnetization. So this HC is very important, and it depends, you see immediately, on the anisotropy constant. So the largest anisotropy, the largest coercivity. So the largest anisotropy, the more hard is your magnetic material. This is, of course, important to remember. On the other hand, it will be reduced by MS. This is kind of maximum coercivity that we can have. Why? Because we considered in this model only a single domain particle. So if we introduce domain walls will always lower this coercivity. So what does this again mean? That if you want to have a very hard magnetic material, then it would be perfect if you would have grains which have a size of the single domain particle, so that each grain is a single domain particle. And this would be your perfect hard magnetic material, because then you can go to the maximum coercivity that you can theoretically reach from the intrinsic properties, because extrinsic properties will always reduce your coercivity. Okay. It's quite late already. I spoke already 1 hour. Okay, but I will go on quickly now. So next concept, immediate concept, is superparamagnetism. Superparamagnetism means simply that you have a lot of single domain particles, but now not as I imagined my perfect permanent magnet. They are not in contact, but they are not interacting in this case in the superparamagnetic material. So let's imagine them that they are not that close, that they are a bit far away from each other. In this way, this material will behave as a paramagnet with huge single magnetic moments. So this is a super paramagnetism with a huge susceptibility. And you can imagine that this is important in magnetic recording, because in magnetic recording, if you think about a hard disk where you store your single bits in tiny magnetic areas, then these magnetic areas, of course, should not interact one with each other. Otherwise, you would cancel the information that you would like to store on it. Now, each single area should contain a single bit on your hard disk. And this brings us immediately to a problem, because in order to make your material, your information stored stably on this hard disk, now you have to make this single area here very stable against being magnetized in different directions. And how can you do that? Increasing, of course, the anisotropy. So if I increase anisotropy, coercivity will be higher, and it will be difficult to magnetize the material in a different direction. However, another thing is that we want to reduce, of course, the size of this area of this single bit, because the more it is reduced, the more bits I can store, the higher is your storage density. and this is the so-called superparamagnetic limit, because since the anisotropy energy is a volume energy, if you reduce the volume of your single bit, then you reduce this energy that stabilizes the magnetization of your single bit a lot. And if you reduce it too much, then it becomes comparable with thermal energy. And this would mean that only thermal energy, only temperature will move this magnetization direction continuously. And then you don't have a storage anymore of your single bit. So nowadays we found ways, of course, to overcome these superparamagnetic limits. We are far beyond the superparamagnetic limit, but only because we are using very special techniques. Now we moved away from single bits on your hard disk, which are stored in the plane, so which have magnetization in the plane. Nowadays they are pointing out of plane, and this out of plane anisotropy is even stabilized by some underlayers. So now this super paramagnetic limit is overcome, fortunately. Last two slides. Can we observe domains? And of course, this was done already a very long time ago, observing domains. And this was something that I told you in the first lectures. Now, one of the techniques in order to observe magnetic field, and also of course in this way observe somehow domains, is the technique using a fine powder of ferromagnetic material, of iron powder, for example, no? And then they will align along the field lines. So they will align along the stray field, and this is called nowadays the PhD technique, and it's very sensitive to weak fields. Nowadays we use a colloidal suspension of magnetite particles, very tiny magnetite particles, but of course they will indicate you the stray field. And stray field, very often you will have where we have domain walls. So they will show you domain walls and not directly maybe the domain. Another possibility, of course, to image stray field is the magnetic force microscopy, much more sophisticated technique. This is based on the technique on an AFM, an atomic force microscope, where you have a cantilever which is attracted by the atomic forces of the material. And if this cantilever has a magnetic tip, then it's attracted, of course, thanks to the Faraday force, by any field gradient that you might have on the surface. And this again is very sensitive to these stray fields that are coming out from your material. Then you might have scanning electron microscopy with secondary electrons, which are absorbed and re-emitted. And again, this is sensitive to the stray field, but SEM can be also sensitive to the magnetization direction in your material by using backscattered electrons, and sensitive to the magnetization direction, or let's say the total induction in the material, is also TRaMM, which is the tunneling electron microscopy. And here electrons are deflected due to the Lorentz force. These are techniques that are not so easy to use with magnetic materials, because you have to consider that in a TRaMM, all beams are focused by lenses which are magnetic lenses, of course, so you have already a lot of magnetic fields, and bringing inside magnetic samples is not so easy always. And then additionally, of course, we can use techniques like XRT or Newton diffraction in order to understand something about, for example, lattice distortions connected to the magnetization. And one of the most used techniques, because let's say among the most simple techniques to observe domains, is magneto-optics. And if you come to our lab visit, then you will see this Kerr effect magneto-optics. So it's called MOG. This is the effect that we discussed already in the introduction of magnetism, based on what was found by Faraday, which is the rotation of the polarization of light when it interacts with a magnetic material. So the optical constants depend on the magnetism. The Kerr effect we can have in different situations. So we can have a polar Kerr effect or a longitudinal or transverse Kerr effect. They are distinguished by the direction of M. So if M is pointing out of the plane of your material that you're observing, then we speak about this polar effect. If it's in the plane, then we speak about the longitudinal or transverse. And again, of course, you have this rotation of polarization of light. So you need some filters, and you can imagine this effect as an effect of the Lorentz force again. So if you have electrons here that will be moved by this electric field, then they will be deviated by a magnetization or a magnetic field that you have. So in this way, you can image domains, but also domain balls. Both of them, this depends on the mode that you're using. And with this, I finish my lecture, and this is the summary of what you should have learned in this lecture. So these are the famous questions. Please give again a look to this. And you can see here the book that I again used to prepare this lecture, and you can see the experiments and videos. And I did not show you the video of the MOG, but I think if you come to see our lab, then you will see this much nicer than I have here on my computer live. So I hope that who is in Turin will come to visit us and see the labs. Okay, if do you have some questions? I will stop recording now.